So this part is review, but we might be a little rusty. So I have already labeled these sides. Let's erase them and go back and relabel them. So looking from the given angle of 30 degrees, this side is the opposite, this side is the hypotenuse. We reviewed. Sine of theta is the ratio of the opposite side to the hypotenuse. So we could set up this equation. Sine of 30 degrees is equal to x over 10. And all we would have to do is multiply both sides by 10 to solve. And we would get 5 is equal to x. You can punch this part straight into the calculator. 10 times sine of 30. Now, the other thing you might remember from the previous course, if this is 30 degrees, that makes this a special right triangle. The short leg is x, the hypotenuse is 2x, the long leg is x root 3. So if the hypotenuse is 10, then the short leg would have to be 5, and the long leg would be 5 roots of 3. Okay, so you might remember that. What was the other special right we studied?
Like 45.
Very good. A 45, 45, 90 right triangle. So whatever one leg was, the other one had to be the same because they're congruent. And the hypotenuse was that length times the square root of 2. Okay, so this first problem you could have solved either using right triangle trig or what you know from special right triangles. Okay, now the second one, we can't use special rights because 25-degree angle is not one of those special ones. So we would have to use what we know from right triangle trig and set up that trig equation. From this angle, this side is the opposite, this side is the adjacent. You always label what you want and what they gave you. So which of these three trig functions is a ratio of opposite and adjacent? Opposite and adjacent is tangent. Now remember, SOHCAHTOA is our mnemonic that helps us remember. Okay, so tangent of 25 degrees is equal to the opposite side over the adjacent side. So to solve for x in this problem, we would just multiply by 10.2. Okay, so pull out your calculators, multiply 10.2 times the tangent of 25, and do you get approximately 4.76?
Yes, 4.75.
Okay, so that length is approximately 4.76. All right, these skills that we're reviewing here are necessary for some of the problems we're going to do for homework. That's why we're reviewing them. All right, the last one, our 40-degree angle here, and this relationship adjacent and hypotenuse would lead us to cosine. So cosine of 40 is equal to the adjacent side over the hypotenuse. So to solve this one, we would just multiply both sides by 8.
6.13.
And you do get approximately 6.13. Nice job. Okay, so that is just a quick review of how to solve for a missing side on a right triangle when you're given an angle and a side. Okay, now, when can we use Pythagorean theorem? Because I didn't try that on any of these. When can we use Pythagorean theorem? What do we need? Yes, sir?
We need 2 sides.
We need 2 sides. Okay, so if we have 2 of the sides, we can use the Pythagorean theorem. All right, take just a moment. Talk amongst yourselves. How can we prove that all circles are similar? Go.
It's all different, the same thing. I know what you're saying. I know the focus don't. The way you said I need points from the
Okay, so I'm hearing some absolutely accurate statements out there, which is very exciting. First thing I heard describe that. Okay, so, so that's the first thing I heard. And then over here in the Macklin area, I heard exactly what I was looking for, and I heard it again here, that the ratios of all the links, the ratios of all the measures are equivalent. And with similar figures, aren't our ratios of the links equivalent? And that's exactly what we're looking for here. So let's prove it. Let's start off with those sweet little radii. All right, what's the radii of the smaller circle? R1. Yes, it is. All right. So R1 and the larger circle? R2. All right, let's think about another measurement we know about circles. How about diameter?
R2 first.
Okay, so if the radius is R, what would the diameter be? 2R.
That's what I meant, 2R.
Oh, that's a 1, not an I. And then what would the diameter of the larger one be? 2R2. Okay, what's another measurement we know? How about another measurement of length, circumference? Distance here? Okay, and let's see what we remember. What's that formula?
Pi squared.
Oh, you started off right. You said 2. So 2 pi r. There's no squared because square indicates a second dimension, and now we're thinking about instead of a length, we're into area. Okay. Okay. So they don't all look the same right now, but watch this. Don't the 2's cancel? Oh, so we have R1 over R1 and R1 over R1. Oh, don't the 2 pi's cancel? Yes. And so every single ratio is the same. Yes.
Okay, so also when you're doing circumference, can you just do like pi times diameter?
Yes, pi d is our other one.
Okay, that's good.
You are correct.
Okay.
All right. What I want to take just a moment and stop and go look at is the calendar I gave you all. So we are finishing up geometry this semester. So we started off with that probability unit because it was the one little unit that didn't flow with the rest of them. So the rest of what we're studying this semester is truly aspects of geometry. So today we're revisiting circles, and we're going to look at regular polygons, which is one type of polygon that you guys didn't study the area of in middle school. You know the area of a triangle, half base times height. You know how to find the area of a rectangle, length times width. You know how to find the area of a trapezoid, half the height times the sum of the bases.
Right.
So these figures you've studied. Today we're going to look at regular polygons, which is new to you. And you had to know trig to be able to do it, which is why in 7th grade, when you studied all of the rest of them, you didn't do regular polygons because you didn't know trig. Yes, ma'am.
Did we ever learn about circles?
You did in 7th grade.
And before that.
Yes, she did, because that's who my daughter had. And I followed her assignments. So, all right, so here we go. These are our standards that we'll be covering. First, today we're going to look at circumference and area, and basically be able to define how these formulas came about. Then tomorrow we're going to start in with volume. We're going to look at cylinders and prisms tomorrow. Monday we're going to look at pyramids and cones. We're also, and I spelled this wrong. I spelled it cavalier. I did not. I actually spelled it cavalieri, but it auto-corrected. Pretty cool, huh? And then the last thing we're going to go back and do, I'll correct that before the day's over, is look at the volume and surface area of spheres. Now, in 7th grade, you studied surface area. So we're not going to go back and do surface area of cylinders and prisms, and we're not going to go back and do that. But you didn't study surface area of a sphere. That is new to us now. So that's why we're tackling surface area right here, just so you don't leave high school without ever seeing it. Then we're going to do some application, which is pretty cool. Because the rate, and there's anyway, we have some cool stuff, which you can actually do some real life math with. And then, this is a whole unit, but it's only 7 days, so we're not having a test, we're just gonna have a quiz. Yes, ma'am?
Oh, the little tissue box thing, do we use that for the shoe net?
The little tissue box, we don't need yet. That unit got moved. It used to be at the very beginning of the year. It's been bumped back a while, but if you brought your tissue box in already, we're good. I'm storing them. I'm storing them for you. Okay. All right. So that's why I'm jumping into circles today, which seems a big leap from probability. Yes, it is. Probability was pretty much all its own little self, and then the rest of the semester is geometry. All right, so circles, similarity. Now, we know other ways to prove similarity, and that would be transformations. Do you remember transformations? Translation. That's where we slide. Rotation, reflection, and then the one transformation that doesn't produce congruent figures is dilation, right? And what does dilation produce? Similar figures. So, we proved circles were similar with their ratios. Now let's prove circles are similar by writing a composition of transformations. And let's think about which transformations we need here. If I were to rotate a circle, would it appear to be different? No. So will a rotation really help us? No. Okay. If I were to reflect a circle about its center, would it appear different? No. So we really don't need the rotation or the reflection. What we can use, though, is we can move the circle around, translation, and we can blow it up, or we can shrink it. We can reduce, expand, or shrink. What do we call that? Dilated. Okay. So all circles can be proven similar using dilations. And when we write our rule, it's going to be a combination at times of translations with dilations. So we have the little red circle here. We have the big blue circle here. All right, so if I said the red circle can be described as all points xy, what can I do to that to create the blue circle? So right now the red is hanging out at the origin. It has a radius of 1. The blue one is hanging out up here at 3, 3, and it has a radius of 3. So how would I need to dilate the red circle to create the blue one? Multiply by 3. So that's what we do first with our rule here. We would say, okay, we have to take all those points and triple them. All right. Now what I've done is created a bigger red circle right here at the origin. How do I get it over here?
Translation.
We have to do the translation, which will move it right 3 and up 3. Did I write a rule that took the red circle to the blue?
Yes.
Yes. Did it consist of translations and dilations?
Yes.
Yes, those circles have been proven similar. If we can write a composition of transformations, we have proven similarity using coordinate algebra.
So we can't.
Okay? Now, let's go over the rules for dilations. We have to be careful with dilations. For a dilation to occur, the center of dilation needs to be at the origin. So, if the center of dilation doesn't begin at the origin, that's our first move, back to the origin. Because if we just multiply when it's not at the origin, we will get a figure that's been stretched in different directions. So, first thing, move it back to the origin, then we'll dilate, and then we'll shift it to the new center. All right, so if you were to do a circle with a center at the point 2, -1 and had a radius of 10. So this is our original circle. It's a circle with a center at the point 2, -1 and has a radius of 10. So to begin with, this circle is hanging out right there. We're supposed to prove it's similar to a circle with a center at the point -3, 5 that has a radius of 2 by writing the a composition of transformations.
So do we move back?
Okay, so every point to start with, every point on the circle has to be shifted to where the center moves to the origin.
So we'll subtract.
Okay, good.
And it's add
X minus 2 and then y plus 1.
And then y plus 1. Okay, so that's what we've done first. We've taken this circle and shifted it to where its center now lies at the origin. Now we have to do the dilation. We're going from a radius of 10 down to a radius of 2.
we divide by
We're dividing by 5.
Yeah.
Okay? Dividing by 5 is the same as multiplying by what?
1/5.
1/5. So we'll multiply 3 by 1/5. Alright, so let's do it. 1/5 would create 1/5 x minus 2/5. And 1/5 y plus 1/5.
Okay. And that's the dilation.
Okay, so now we have dilated. And in this case, it caused a shrink, didn't it?
Right.
Alright. Now my new circle has a center at -3, 5. I am now at the origin. I need to go to -3, 5. What can I do to this to get to -3, 5?
X plus 3 and y. Yeah, it is. It's X plus
It,
Oh, it's
it's-
minus.
X minus 3.
minus 3
I didn't say
and
y plus 5.
plus 5. Okay, some of us don't like fractions. I'm cool with that. If you don't like fractions, think of this as -0.4 and think of this as +0.2.
That's good.
I will allow you to use fractions and decimals interchangeably if it is a terminating decimal. Okay? Alright, so 1/5 x, -0.4 and -3 is -3.4. And then 1/5 y. And then 5 plus 0.2 is 5.2. Okay, we wrote the rule. So if we can write a rule that only consists of translations and dilations, we have proven similar figures using coordinate algebra. So we can prove it algebraically with ratios or with coordinate algebra by writing a rule. Yes, sir?
You have to move it to the origin before you write your rule.
You have to shift the center to the origin before you dilate.
Is that shift to the origin in your rule also?
It was, because my original circle started off at 2, -1, and so this step right here shifted the original to the origin. And then this step right here shifted it from the origin to the new center
After the dilation.
after the dilation. That's right. So this was where our dilation can.
So does it? Do you want us to? Well, because on here it says to prove that is something. To,
Similar? Okay, this, if it looks like a little tilde, the tilde is a mathematical symbol that means similar. Did y'all use that last year when you were studying similar triangles?
Yeah.
No,
Okay.
And then what the line.
And then if we have this with the equals under it, it doesn't mean similar, it means congruent. Okay. Certainly.
We're all buying now.
He's got throw up in there.
It's fine, just leave the door cracked.
You look so sick.
Don't think.
I'm
about it.
recording.
Okay. I mean, he looks sick. I'm saying.
Alright. Now, so sticking with circles, we've already talked about circumference once. Now, when we look at circles and we look at their circumference, 1415. Keep it going.
9.
9.
6.
Wait, no. 2.
2 6.
I'm gonna call it 2 6.
Yeah.
I knew there was a 6 somewhere.
Yeah. All right. So, with circles, anytime we take the circumference and divide by the diameter, we get pi, and that's from that formula, isn't it? Yeah. Circumference divided by diameter is pi, and that's where the circumference relationship comes from. All right. So, geometric definition of circles. If I had to define a circle, it is the set of all points in a plane that are equidistant to a given point. And this distance is the radius. And the point that they're all equidistant from is the center. So that's a geometric definition of a circle. It's the set of all points in a plane that are equidistant to a given point. All right, we already know these two things about a circle. The circumference is 2 pi r, or pi d. And the circumference represents that distance around the circle. Also the perimeter of the circle. Don't those two things mean the same thing? Okay. Area is equal to pi times the radius squared. Now that represents space inside the circle. All right, let's check out where this formula comes from.
Video.
Pi r squared gives you the area of a circle. But where does pi r squared come from? First, we'll draw a circle and fill in its area. Next, we will divide it into large equal parts and arrange them in a rectangular formation. As you can see, it barely resembles a rectangle. So next, we will divide the circle into small equal pieces, and we will arrange them in the same manner. You can see that it appears more like a rectangle. So, if we divide the circle into even more smaller pieces, you can see that every time the shape becomes more like a rectangle. So, how small must we divide a circle before we can get a perfect rectangle?
Yes, this is your homework.
Well, we can keep on dividing the circle into small, smaller, or the smallest pieces you can make. But the answer is to divide the circle infinitely many times until we cannot distinguish the lines, and eventually the circle can now become a perfect rectangle. So, the area of the circle is equal to the area of the rectangle, which is equal to base times height. The height of the rectangle, as you can see, is the same as the radius, so height is equal to radius. To find the base, we need to look at the circumference of the circle. And when we compare the base and the circumference, we can see that the base is equal to 1/2 the circumference. Remember that the circumference is equal to 2 pi r. When we combine it with 1/2, the 2's cancel out, and base is equal to pi r. So now base times height becomes pi r times r. Combine the r's together and we have pi r squared, which is equal to the area of the rectangle, which is equal to the area of the circle. So pi r squared can be used to calculate the area of any size circle that exists.